So we want to prove by mathematical induction, right? So meaning you want to ascertain whether a mathematical statement is true or false. And the steps are for you have to show for n equal to 1 and also the subsequent numbers 1, 2, 3, 4 and all of that. Then you now assume for n equal to k. If you assume for n equal to k, you now prove also for n equal to k and the next term, which is k, n equal to k plus 1. So first of all, we say from this equation, we say let n equal to 1. So if n equal to 1 is the first term here, we have what? 1 raised to power 3 equal to 1 raised to power 2, 1 plus 1, 2, all over 4. Alright? So this is 1 equal to, what do we have here? 2 raised to power 2 is 4. Right? 1 plus 1 is 2, 2 raised to power 2 is 4. 4 times 1 is 4, 4 over 1, 4 over 4, it will give you 1. What about the next one? We have let n equal to 2. So n equal to 2 means adding up the first two terms, right? We have what? 1 power 3 plus 2 power 3 equal to, we now substitute the value of n as 2 in this side, right hand side. Here we have 2 raised to power 2, 2 plus 1 power 2 over 4. Right? So here you have what? 2 raised to power 3 will give you, it actually means 2 times 2 times 2, 8. 8 plus 1 will give you 9. Here we have 9. If we simplify this thing further, 2 plus 3 will give you 9. 2 plus 1 will give you 3. 3 raised to power 2 will give you 9. So 9 times 4 give you, that's 6, right? So that's 6 divided by 4 will give you 9. Right? Good. So what about the next term? What about the next term? If you check for the next term, which is let n equal to 3, the first 3 terms again, 1 plus 2, 3 plus 3 raised to power 3 is equal to whatever we have here. 3, 2, 3 plus 1, 2 over 4. Alright. So if we simplify this thing further also, we have what? Okay, 3 raised to power 3 will give you what? 3 times 3 will give you 9. Alright? So 9 times 3 will give you 27. So 27 plus 8 will give you 35. 35 plus 1, 36. So here we have what? 36 equal to, if you simplify this thing further, you get 36. So it is true for all these numbers, 1, 2, 3, 4, 5, 6, and all of the above. To prove it further that it is true for all terms and for all n, you have to assume that it is true for n equal to k, and also for all the n's subsequently coming after k, which is k plus 1, k plus 2, and all of that. So we have to just prove that, once we prove that it is true for n equal to k plus 1, it means that it is true for all n. Right? Now for here, we assume that n is equal to k is true. So this is the logic now. So you'll be replacing, wherever you see this equation, you'll be replacing n for k. So wherever you see n, just put k. As simple as that. From here you have 1 raised to power 3 plus 2 raised to power 3 plus 3 raised to power 3 plus, this is k, 3 equal to k plus 2, k plus 1 or 2 all over 4. Right? Cool. So this is for n equal to k. You now prove for n equal to k plus 1. So for k and also the term coming after k. So prove for n equal to k plus 1. Hence, let's just write out for k. This is for k, right? From here to here. Plus 2 power 3 plus 3 power 3 plus k power 3 plus the subsequent n, right? K plus 1. So we'll be putting the value of k plus 1 here. So we have the next term as k plus 1. Alright? 3 equal to here we have what? K plus 1. And also here we have what? K plus 1. Let me put it this way. Plus 1. All power 2. Right? Over K. So if you look critically, notice that all this that we have here, from this to this place, is the same thing as what we have here. From here to here. And all these things here is equal to this. So you have to replace this as this. So all this is equal to what? K squared K plus 1 all over 4 equal to, no sorry, plus this, plus K plus 1 over 3 equal to K plus 1 squared. K plus 1 plus 1 all squared. Right? All over 4. So to eliminate this 4 here, you need to eliminate this 4. So if you multiply through by 4, this side and this side by 4. If 4 multiply this, you have 4 divided by 4, 1. So you'll be left with K squared 2K plus 1 squared plus 4 multiply this. You have 4 into K plus 1 over 3 equal to, here you have 4 will divide by 4. You have 1. Hence we'll be left with K plus 1 squared. K plus 1 plus 1 all squared. Right? So we simplify further. So they have something in common. You can actually factor out K plus 1 squared. And we'll be left with what? We'll be left with K squared here. And for this place, we'll be left with 4K plus 1. Right? If you use this to open up this, you still get the same thing. So only factor out this. What about this side? This is equal to, we have the same thing here. You can see that they are the same. Because if you expand this, remember that this square comprises both this and this. Hence, all this is equal to K plus 1 squared plus 2 into what? K plus 1 plus 1 squared. So this is the expansion. Alright? So for this is what? K plus 1 squared into K squared plus 4K plus 4. This is equal to K plus 1 squared into, this is what? This is K squared plus 2K plus 1. Right? Plus 2K plus 2 plus 1. Hence, here we have K plus 1 squared into what? K squared plus 4K plus 4 equal to K plus 1 squared. All this is what? K squared. We collect like terms. You have 2K plus 2K, 4K. You have 1 plus 2, 3 plus 1, 4. 4. You can see that what we have here is the same thing as what we have here. The left hand side and our right hand side is true. So it is true for all n. Hence, you say, hence, the mathematical statement is true. So this is how you prove by mathematical induction. Right? You can see how straightforward it is. It's not that complicated. You show for n equal to 1 and subsequent numbers, 1, 2, 3, or 4. Or you can actually show for maybe only n equal to 1. If it's true, you assume for n equal to k. If you assume that n equal to k is true, you now go subsequent and check for n equal to k plus 1. So the next term coming through.